Okay, so welcome to the last lecture. Um, so today I want to give some kind of outlook, uh, right? I mean, so with Dustin's lecture on Wednesday, we kind of finished what we promised in the first lecture. Um, and so today I want to talk about some directions one could go in with the kind of machinery we develop. Um, uh, so maybe, yeah, so some, I don't know, 5 or 6 years ago, like I mean, I did a lot of this p-adic geometry, and like I always wanted to have a way to do this not just p-adically, but also with the real numbers and over big C. But it was always clear to me that I really needed a completely new language to talk about these things. Um, and so this is, I mean, as I said already in my first lecture, this is kind of the reason that I was really putting a lot of effort into this project. And so I finally have the feeling that we're basically have now the language that we always wanted, and then now it is a sensible question to just try to really use it to do a lot of things. And then so it occurred to me that actually, I mean, there was this original goal that I maybe had in mind for what the series should do. But on the other hand, it's also good to look in other areas of mathematics how the theory might be useful. And so I'm not really competent, but I will still want to give some vague ideas that I think might be worth looking at. Okay. All right. So here, yeah, some possible directions, and I will start somewhat from the most well-developed to the most speculative. So something, this is not just a possible direction, but that not just works. I mean, so we do have now a general theory of quasi-coherent sheaves. Not just no finiteness conditions are imposed on the modules in analytic geometry, in all flavors of analytic geometry. And all of these different flavors of analytic geometry are also unified into this one thing, which is analytic state. And what's even better is that this is not, I mean, this is really a full six-functor formalism. Love the theory of the six functions. Upper star, lower star, lower streak, upper streak, tensor, and so on. And this just lets you play a lot. And in particular, like some things we kind of looked at into this, using this formalism is that, well, actually, this sounds stupid, but it's actually, for example, as Dustin explained in the last lecture, it's actually a non-trivial application of this. First of all, a general theory of a structure sheet without any Mysterian or otherwise hypotheses. Where, in particular, like for Berkovich spaces, even those kind of a finite type over the integers, Jerome Poinot had to really work a lot to define such a thing. And even for edit spaces, there were this kind of non-cheafiness issues which are resolving. So,
but you have to define what it derived.
Well, but in our frame, I mean, we just have these analytic stacks. They come with the structure sheet, period. Okay. Then there are all sorts of Gaga theorems that you can reprove, but you can also prove various new sorts of Gaga theorems, actually. There are various results about like descent of vector bundles. And again, this sounds a bit silly, but and for example, there's this famous paper of Grünfeld about like infinite dimensional vector bundles or something like this is called. But in particular, he proves that if you send a ring R to the like vector bundles over R Lorentz series T, so something that arises naturally if you think about loop groups and so on, then he proves some descent results for that. And I mean, it's a difficult paper. And Aki and Messi was recently revisiting this using some of these descendable ideas. But just a few weeks ago, Chesnevicius was asking me about yet another variant of that kind of result of Drinfeld, and whether our technique could be useful for proving it. And I think they are, and there's just a very simple proof using this kind of general formalism that we have. That it's very easy to prove such statements. And then we also, like in our complex course on complex geometry, we discussed like Hertz working on for complex manifolds and such things that kind of one can approach using this. One thing which we in some sense still haven't quite figured out, but we're quite optimistic that in principle could be done, is also to prove the Atiyah-Singer index theorem using our technology. Related to these last points on Riemann Rochen and Atiyah-Singer, I mean, they are, of course, very, very closely related to the notion of K-theory. Right, and so one thing that was kind of missing for a while is the notion of the K-theory of analytic spaces. So in like an algebraic geometry, this was defined first by Cole and then for general schemes by Thomason. And it really uses that you have a well-behaved category of coherent sheaves on it, and then maybe, I mean, actually stable infinity category of perfect complexes. And then you can define the K-theory of that. But going to analytic geometry, there was the issue that there is not a good enough category of modules of which you could then take, apply these categorical techniques and get some kind of K-theory. Using our technology, you can actually do it. You actually don't use exactly that those quasi-coherent sheaves that's there, but some variant of nuclear modules. But this has now been analyzed to some extent. So this definitely uses the work of Sasha Efimov to define K-theory of dualizable categories. And then if your analytic space are actually adic spaces or Tate adic spaces, this is what works out in the PhD thesis of Grigory and Andreyshev. And there, we had some problems at first to define this over the complex numbers, but also some ideas how to do that. The gaseous theory might actually also help for this. There are actually also some other relations to the work of Sasha Efimov. So he has these very strong results about the category of localizing motifs, so proving that it's a rigid category, particularly generalizable itself. And using this, you can actually define certain refined variants of cyclic homology, topological cyclic homology, and so on, that are actually not taking values in some kind of complete category, as usually when you take S1 fixed point, you get modules over some power series ring, which are complete. But instead, you can go to nuclear modules in our sense again. And so this ties back in this that theory again to our kind of analytic geometry. Let me mention maybe that if it's okay, Dustin, that Dustin has a joint project with Brooklund, where they use some of this nuclear K-theory to settle some like questions like chromatic homotopy theory.
Oh yeah, but we figured out how to avoid it actually.
Okay.
Yeah.
Too bad.
Yeah, I was a bit disappointed too, but yeah.
All right, so that may be where I'm kind of coming from and where there's a lot of applications and where really a lot of work that's already been done is in the area of like theoretical homology theories and so on. So And there was this prismatic homology, and then which was defined from homo schemes. And one question that people had was how to really define it for the rigid non-generic fibers. And this then very much is related to analytic stacks in our sense. So in particular, there is now what's called the analytic Ram stack, defined in the work of Rodriguez Camargo. So which gives you a way to talk about six-functor formalism on what's classically known as like D-cat modules. So there's a certain completion of the ring of differential operators, giving some kind of differential operators of infinite order, defined by Ardakov and Watzlaw. And then they suggested that if you work some on P-adic analytic geometry, you should really look at these modules over these D-cat modules and try to get a six-functor formalism for that. But as usual, I mean, you run into some kind of function analysis issues doing so. Yeah, but using our analytic geometry, you can really handle this. And Rodriguez Camargo was able to write down, I mean, in some sense, by specializing the six-functor formalism to specific stacks, get a very general six-functor formalism for these DK modules. So this relates to D modules. There's also in the P-adic world the analog of like Higgs bundles, and so some kind of Simpson correspondence. The first incarnation of which goes back to Deninger, Werner, and Faltings. And so these can also be interpreted as like in terms of a stack. And so that's this so-called analytic or state stack. So this you can find in particular, there's like, okay, maybe not yet using our technology, just essentially it's work of Anschutz, Heuer, and Lebras. And Heuer in particular has recently obtained really strong results on the P-adic Simpson correspondence. And this work on these hot state stacks is also very closely related to what's known as geometric sense theory. So this is something that originally arose from sense theory, which is something about P-adic Dollar representations. And which has been used to very great effect by Louis Kahn and also Rodriguez Camargo. For applications to P-adic modular forms, P-adic automorphic forms. So also last Friday, Vincent Piloni gave a talk about his joint work with Boxer, Calgary, and G, I believe, where they prove modularity of genus 2 curves over Q in many cases. And some of the key technical part of this proof is really using this kind of technology. And what all this is pointing to is really that there should be some version of like P-adic local lengths for local analytic representations. Yeah, in terms of some kind of geometric lengths on the Falcon curve. So some P-adic version of what I did in my paper with normal thought. Yeah, but also mentioned here. I mean, there's something that's in some sense combining, or something it's different. The ROM and state spectrum and so on is also from analytic prismatization. And with all these people that I mentioned, there's hope that one can formulate such thing. which is maybe the proposal for something in this direction. I mean, this proposed by Hellman, and by Emerton and G. Something in this direction. And so, I mean, this, of course, maybe what my original interest is. There was this work with Spark on geometrization of local langnans, and I would like to formulate all inclinations of local langnans in such terms. And eventually then also global langnans. And so this is to a large extent, I mean, at least work in progress, and this is probably already very speculative, but this is something that's very actively investigated. And so actually, a lot of progress on this was made during this Hausdorff trimester that happened last summer here in Bonn. And in particular, we discussed a lot about these things. And then at some point, we realized that now that we understand this Felix story really well, and that we understand the kind of correct geometric language to phrase these things in, we can just basically one-on-one translate all the ingredients in the periodic world to the real world. So there's a real analog of virtually everything that's happening in 3. So there's also an analytic around stack. And there's actually a funny version that is actually isomorphic to the Betty stack. As it so happens in this case, where this is some incarnation of a Riemann-Hilbert correspondence. You can also define an analytic Hodge stack, which in this case actually maybe there's some kind of, here it's a non-trivial gerb. I think here it's a trivial gerb. Okay. And again, there is this analytic prismatization is a low path on time curve. Also here you can define, I don't know. Yeah, so there's also some analytic stack. So the analytic prismatization in some sense encodes, the vector bounds on it encodes some kind of periodic variations of Hodge structures. And so there's also an analytic stack encoding variations of twistor structures. So, I mean, of course, this ties in very well with all the work of Simpson in this world. And then Mochizuki really developed this series of variations of twistor structures, which are a generalization of variations of Hodge structures. All right. Oh. There's a certain action of U1 on these things as U1 equivalent objects. And then it seems to be possible to synthesize everything and also get a formulation of real local langlans, like the local langlans corresponding for like real Lie groups. Yeah. For some kind of locally analytic representations. Some groups G of R.
Can I ask a question?
Yes.
Can you produce the weight filtration too in the analytic stack?
It's a very good question. Let me comment on this in a second. Not yet. But okay. Some kind of geometric langlans on twist of V1, which is the kind of real analog of the far function. So I gave a talk in Münster 3 months ago or so, where I was outlining the general form that this should take. And I will give some 3 lectures actually in Princeton a month from now, where I'll maybe say a bit more about how this is supposed to work. Actually, part of this, again, it's maybe a small thing, but maybe not. I mean, so usually when you talk about representations of G of R, you run into all sorts of functional analysis issues again, and usually you replace them by a more algebraic notion of these Harish-Chandra decay modules by passing to the vectors, finite vectors and some compact subgroup. But then the theory somehow less invariant because you needed to choose this K, and well, it becomes more algebraic. But in our world, there's really not much of an issue of really encoding representations of a real group direction. But we don't need them.
But you have many representations which have the same Harish-Chandra modules because you can use different function spaces, different spaces.
So maybe as this question comes up, so what we'll actually do is we will look at the real group. It's a real analytic. It's a group object in real analytic manifolds, and so you can do the kind of real analytic inclination as an analytic stack. And so this is a group object in our analytic stacks. You can take the specifying space of this, or yeah, let's say space.
Okay.
Let's guess these complex numbers. Mod that. Are real. And so, I mean, as usual, like sheaves on a classifying stack, they are something like representations of the group. But to realize them as representations, you need to go back to the point where, and there are 2 functors. So there's a projection from the point to here, and you can take either pi upper star or pi upper streak. And like for any of these usual GK modules, there's a canonical object in here actually. And then the pi upper star should, I mean, this is something we haven't checked yet, but the pi upper star should produce a minimal globalization, the pi upper streak should produce a maximal globalization.
So what C you take? You take C with the gaseous?
Yeah, you can take the gaseous structure, it's good enough. Yeah.
And so you have of course, this is closely related to some results on existence of analytic vectors in representations. You should, otherwise you would not. Do you use such? I mean, the fact that there are enough analytic vectors.
Let me not try to say anything precise about this relation here because it's something I still need to think much more about. Right. So there was this question about wave structures, and I believe it's related to the following. So now we run into the speculative realm, really. So for these things, I'm pretty confident that some version of this will work out. This is at this point more of a speculation, but I have a very strong belief in it, but it's a speculation. So classically, in all sorts of questions about functional analysis and I don't know, complex geometry and everything, you often really need to put metrics on something. Like if you really want to prove a Hodge decomposition at some point, you need to do some L2 stuff, put metrics on stuff, and so on. This is something that we cannot yet incorporate into that we cannot yet translate into our into our world, everything that's related to metrics at this point. But I believe it's clear where to look. Namely, you should look at this extended Berkovich line that we had. I will connect this in a second to this question about weight structures. Okay, so recall this Berkovich space, and maybe the way Dustin was drawing it. So you have some kind of central point related to like rational numbers, and then there was a ray, let's say for Q2, and then at the end of this you have kind of F2, and then there was a ray for Q3. At the end of it you had F3, and all the other primes, and then there was also the Archimedean prime corresponding to the reals. And now usually, like in the Berkovich space, this kind of ends in the middle because you ask for a triangle inequality. Well, we don't have to do that. And so there is no point at infinity here. And so there's this point at infinity. And I mean, our Kirchhoff geometry kind of tells you that this point must be related to metrics. And to some extent, you can already see that, like when you, but just some fragments of it. But also by analogy here, like if you work two-adically, then like extending over this point precisely means that you put some kind of like a vector bundle over this thing. It's like a Z2 module over the integral two-adic numbers. And so you're extending over this bunch of p-adic places is definitely putting some p-adic metric on things. And so it's very sensible to think that whatever exactly happens here, it must have something to do with putting metrics. Metrics on some kind of real stuff. Yeah, so some question we have in our mind is whether there is a way to like prove the Hodge decomposition, like for complex scalar manifolds or something like this, using some geometry that would involve this extra point here. In this abstract language, this is kind of difficult for me to think about, but we actually have a very good analogy. Again, I mean, we can again use this analogy between 3 and 4. So theoretically, so I said that there's something about local analytic representations. And so if you work over this kind of theoretic part of this picture, then over this part of the Berkovich space, like over the open part, you can define a complex analytic space in our sense called QP locally analytic. This corresponds to the union over p to the n minus p times ZPLA, where ZPLA it really gets the analytic spectrum of the locally analytic functions from ZP to QP. So those ones that are locally developable, you can locally develop into a power series expansion. And this kind of comes up very naturally in all of these investigations there. And we know that this analytic space, which lives over the open part, because naturally it has QP coefficients, this has a canonical extension. Over the F2 point. And so this is very much related to a theory of locally analytic FP long series Q representations. I mean, these are the coefficients of p-adic groups of some V of QP. At least some fragments of which you can find somewhere in the literature. So periodically, there is some kind of, so this canonical extension is actually a little bit subtle to write down. It involves some kind of divided colors. But existence is very important for this periodic story. And one thing this suggests, and which I don't yet know how to do, is that if you look at the real part of the picture, it's the real, and then it's funny closed point in infinity. Then over here again, you also have the real numbers, like as a real analytic space. So this the thing that's covered by, yeah. So there's R as a real analytic manifold. And again, you locally, the thing with the functions are the real analytic functions. So the ones that are locally developable and locally be developed into power series expansion. There's something that maps to the base, and I mean it maps to the open part of the base. But like each fiber over a point is this one. And it suggests that this should extend canonically over the function. Yeah, canonically over the closed point in infinity. In a way, I don't yet know how to really think about. But this also suggests that if you have some like, I mean, if this could be done, and this would be some kind of ring object, then also this real analytic group, which lives over like our gas, this should also expand. Canonically.
So here you use the gaseous, at all points you use the gaseous structure or use liquid for different?
No, we don't. I will come to liquid structure later today. For now, it's not needed for anything.
So you just use the same at all points of the.
So acting on this again, you have a rescaling action. So there's a lot of different copies of the real numbers now. Sorry for that. You have a rescaling action of the norm, and everything will be equivalent to that.
But and it maps to the Berkovich, in your sense, to the Berkovich space. I mean, to the analytic stack of the.
Yeah. So this maps to the space of norms, yeah. And it's an open subspace of the space of norms. And over there you have this analytic stack, which is like the real numbers of the locally analytic, real analytic thing, which lives a priori over the open part, over the open ray, but then there should be a way to canonically extend this to the point of infinity.
But properly speaking, you mean RLA cross 0, 1, right? Or 0. Yeah.
Yes, yeah, they need.
Yeah.
And so I expect that whatever kind of group that is, and maybe representations of this have some kind of metric structure attached to them. I don't really know. Like that, if you want to extend representation over the open part of the function, I would expect that this is something to do with putting a metric on it, but I don't know. These are some objects that also exist that I don't yet know. Right, maybe let me mention. I mean, also, I mean, this is something like, I mean, you can also just try to understand, like, we can look at analytic stacks over the space of norms that really map to this closed point at infinity and try to understand what the kind of geometry is there. And there's some very peculiar geometry where it's still about some kind of real complex manifolds or something like that, but you are able to localize much more. You're able to really zoom in infinitesimally into your space. And so I think it's very interesting to try to investigate what geometry over this point looks like more broadly. So we can zoom in. Yeah, and sometimes infinitesimal. It's a very different type of geometry. So I mean, you have to, for example, you have to use a Riemann sphere, and then the bounded part of the Riemann sphere is actually just what seems to be just a closed unit disk. The bounded part is some kind of weird overconvergent, minimally overconvergent neighborhood of the closed unit disk. Bounded is essentially just a closed unit disk. So any real number that's bigger than one is an unbounded function on this thing. So I think it will take a while to figure out how
Why
to.
do you picture the sphere? Sorry, Peter. Why do you picture the sphere?
I mean, actually, we were always looking at this normal like P1, right? P1 maps to zero infinity.
Yeah.
And the P1 over like this whole part still lives over the analytic spectrum of our gas. So whatever happens over this point, it's still happening also over the gaseous reals, but then you can do some kind of final localization there. So particularly, I can take the usual P1 over the gaseous reals and base change it to here, and then look at what the bounded part is, and it's roughly that.
But if you remove the colored part, is it conformally equivalent to the parallel plane?
Does it come from any? Sorry, I didn't catch the question.
If you remove the colored part, is it conformally equivalent to the upper half plane?
Upper half.
Random question.
It's not really base change from anything over here. No.
Okay.
All right, so I think that's an extremely fascinating prospect to investigate this type of geometry. And yeah, as I expected, it should be related to all these questions, but usually you put metrics on stuff. All right, so that was 5. 6. So like one key thing that our formalism allows you to do is really make situations where you have to do both functional analysis and use like fancy category theory. But at this point, you can go completely fancy. So I mean, so there's a theory of fields of higher categories. Or analytic stacks. So, like to any affine guy, I mean, we can first associate just the derived category, but then we could also associate module categories over it. But then, as I was explaining last Friday, there's a theory of presentable infinity n categories for any n due to Stefanich. And so you can just iterate. So you can do 2PRLA and just continue forever. And I mean, so you can define NPRL on X for any stack X. And you cannot just define it, but again, there's some, you have all these kind of 6 functors on it. And so you can just play with it. So the existence of this is not a speculation, but what comes next is definitely a speculation. So I have a strange project with Stavros Galfanidis and Don Zaghi where they're computing some quantum Chern-Simons invariants, and I don't know what they are. But they seem to get certain power series that seem to be very related to the kind of periodic structures I'm seeing. And for a long time, I'm trying to make sense of whatever they're doing. And But now recently I realized that I'm able to think about higher categories, and that, well, the cobordism hypothesis tells you that these kind of topological quantum field series, they should really just be certain higher categories. And then I try to understand which one they should be. And you can essentially say it, but it doesn't quite work. So here's what's called, I don't know, quantum transimus or something like this. I mean, you must be aware that I'm saying words that I don't understand. Okay, so to the extent that I understand anything, you have maybe start with a complex B group, and maybe for simplistically simple or something like this. That's relevant. And then you fix what's called a level. I mean, so there's this funny computation that if you look at, like maybe, I don't know, let's assume simply connected. So then the first interesting cohomology group of G is a third cohomology group, which, I mean, is a simple assumption, has homomorphic to Z. And yeah, so let's fix the level, which is just an element. And so here G is just considered as a topological space, but then you also have the kind of classifying space of G. I mean, G maps to B cubed, so this is if you want the map from G map into this threefold classifying space of Z. This actually D loops, it's a map of groups automatically. So some abstraction magnitude, so it gives you a map from BG to B4 to the Z, to the 4Z. And then, but you can also restrict that to G as a real analytic thing. Right? Because in general, like I had to think that whenever I have a real analytic manifold, it maps to the incarnation of M, like as a condensed set kind of incarnation. And this is basically what I'm using here. And so, but then there's actually, like, okay, so then there's also like the exponential sequence. You have the analytic. Yeah, you have the thanks. You have the exponential sequence. So everything is living here over, like, let's say, guess these complex numbers. And then there's a composite map to be to the 4 of GA vanishes because like the coherent cohomology is trivial. And so it actually lifts the B cubed of the analytic GM. And of course, the analytic GM maps to the usual GM. So now this sounds really like the analytic. All right, but so what does it mean to give a map to B cubed GM? Well, in some sense, it's too hard for me to think about, but so map to BGM, well, that's just a line bundle, right? So BGM, that's just a classifying space for line bundles. Then B square GM, this is somehow giving you some I algebra or something. So this is giving you a twist of the category of modules. And then B cubed GM, this means that you give a twist of the category of categories over it. Yeah. So this map called alpha from BG incarnated as a real analytic group to B cubed GM specifies a twist of like PRL over BG. Okay. I.e. some, let's call it just L for invertible. This invertible object is a 2PRL over this guy. Okay, that invertible object. All right. Okay, so you have this, and you have the projection just to the point. Sorry, the point is like, I guess it's complex numbers. And I think what people do is like, okay, so they want to look at like some family of G torsors, like bundles with a flat connection or non-flat connection, or whatever. And so, but sometimes twisted by this alpha. And so, I mean, this is somehow more or less governed by pulling back this L under alpha. But then they want to integrate over the space of all G torsors. So basically, they're taking this Euler star alpha upper star. And actually, if G wants a finite group, that's literally what they're doing. As I learned from a paper of Fried, Hopkins, Lurie, Telemann. And so, I mean, this just makes sense. And it gives you an object in 2PR. Let's look at the numbers. And then you can wonder, like, so this guy here, it's some symmetric monoidal infinity 3 category, right? N categories form an n plus 1 category. And I mean, quantum Chern-Simons theory should be a 3-dimensional topological quantum field theory, whatever that is. So it should be a by the cobordism hypothesis, it should be a 3-dualizable object somewhere in a 3 category. So now we have one. So the question is this 3-dualizable? And as any expert would immediately tell you this, there's no chance of working. Because the space of conformal blocks, I believe it's called, there you must put some holomorphicity constraint, and I'm kind of not doing that here. But I mean, in some sense, it's not so far. So, but it is 2-dualizable. I think that's for this you don't need much. Okay, so I didn't carefully check that, but I believe it is 2-dualizable. And to check that it would be 3-dualizable, and for 3-dualizability, you would need the following things. You would need that pi is kind of homologic, proper, and smooth. The diagonal of pi, homologic, proper, and smooth, and the diagonal of the diagonal of pi, proper and smooth. So there are 6 conditions to check, and only one of them fails. Okay. So more concretely, this is like the point, not G real the point. This one reduces the exchange to the group being proper and smooth, and this means that the inclusion of the point into this. So for all of these, you would need that they're proper and that they're smooth, homologically smooth in a sense. Any guesses for which of the 6 fails? It's actually the one you probably would expect the least. It's the smoothness of this map.
The smoothness of the second.
Yeah, only smoothness of the RLA.
Just a digression. The map to B, you said that it lifts to a map from B4Z to B3GM analytic, but you wanted BG locally analytic instead of BG. So the obstruction is something having to do with cohomology, with coefficient in something like continuous cohomology, but it is in your language. So I'm not sure what it corresponds to, but
it's just the coherent cohomology of the stack, basically.
What?
Basically, just the coherent cohomology of this stack.
But it is not true for BG itself that it lifts, only for
no,
BG.
because this, I mean, here would be the coherent cohomology of the kind of condensed set stack, which would actually be like the coherent cohomology of this funny stack is singular cohomology. So if you would go here to be for the complex numbers, you would just tend the singular cohomology with the complex numbers. So this one wouldn't lift. You need to go to this.
The obstruction has to do with maps to
before
GA.
GA, right? Yeah. So it's some kind of, I mean, up to this analytic, it's basically coherent cohomology, but on this classifying stack as a condensed set, the coherent cohomology is kind of singular cohomology.
Okay.
And it's because it's a compact group that it vanishes on the when you go to the low analytic. Yeah.
I mean, but the compact is much more crucial for these kind of propositions we can here. Okay, so this doesn't work, but in some sense, I feel like it was so close to working, so maybe you just need to tweak this here a little bit. And as I said in 5, there's actually a canonical candidate where you kind of go to this point in infinity. Maybe that one works. So it's a very naive question. Does it work? Not replacing PRLA by it's fiber, I can say it. Fiber of the extension is the first construction. And it seems weird that this should put the kind of correct holomorphicity constraint into the picture, but I think the formalism might just work out to do that.
I mean, there's also some structure you're not using with the like I think this map to B3GM that you build, it should really have a connection. I mean, I think that you could kind of be going to Deligne cohomology and weight too.
Yeah, so maybe this is not yet completely correct. I just want to point out that, I mean, you can't just play with these things, and you can hope that if you would actually understand what you're really supposed to do, you could write down something that would actually produce something 3D realizable. So, I mean, usually what you would try to do is you would run into all sorts of issues that you always want to do functional analysis and higher categories. And I mean, people manage to do a lot of things, but here you can just very naively try. All right. So this brings me to the last thing I want to talk about a little, and this one I actually want to go into a little bit more details and actually, yeah. I mean, this was very fancy highbrow, and now it becomes a bit more concrete again. So this is about a theory of virtual fundamental clauses.
No, it is. We don't see very well.
It's condensed. Yes,
It's condensed. It'll resolve. Yeah.
Okay. Okay.
So let me ask a precise question, and then I will actually answer it. I mean, so this is a question that comes up in particular, like in symplectic geometry for Gromov-Witten invariants and these things. And that if you are in some more algebraic situation, there is a known solution since some 20, 30 years. But if you're really in the analytic context, it's much more subtle. And one reason I looked into this is because it's a natural, I mean, these kind of things they're doing in symplectic geometry, they're naturally some kind of spaces that are simultaneously kind of analytic, derived, stacky, and so on. And so this is the kind of theory where our situation where our theory should be useful. And so I just try to see to what extent it is useful. And I think it can actually do something. Okay, so let's consider fiber, like the model situation that one's maybe interested in this point. Consider a fiber product of manifolds with M1, M2, M3. 2 x of, let's say, compact smooth, let's say oriented compact smooth manifolds. M1, and 2. Feel free to assume that these maps are closed immersions. I don't think that's relevant. But I mean, so yeah. Consider the final product, but which is of expected dimension 0. In other words, like din M1 plus din M2. So then if the intersection turned out to be transverse, this X would just be a finite set of points, oriented points actually, and so you could count the number of intersection points. Okay. So if intersection transverse, then X is finite and actually also oriented. So any point knows whether it should be counted as +1 or -1. And so you get a well-defined counted signed count of the elements of X. This is a variant under perturbations. So long as you stay, as the intersection stays transverse. And okay, so that's a setup. So what is the question? The question is, can you define the signed count of X in general? I mean, without transverse intersections, purely intrinsically on X.
Of course, every connected component will have a well-defined, like in Fulton's theory, every connected component will have a well-defined number, which is the part of the intersection number coming from this connected component.
Yeah, sure. But even these local ones you need to define, right? Right. So the good situation, I know. I mean, you have two circles meeting transversely, and then use +1, use -1, is intersection 0. But now this might degenerate, and I don't know, you might have two circles that, I don't know. There's some situation like this, where this might be, I don't know, this might, did I have a situation where they equal for well? The one, sorry.
It can be infinitely many connected, like pathological stuff.
So I don't know. I mean, this might be tangent to infinite order somewhere. This might be the same for a while. Then cross, I don't know, all sorts of really funny behavior. And then, I mean, right? So if instead of compact smooth manifolds, you had some kind of smooth projective varieties there, then in this case, it's known how to do this. But also, like, the intersection cannot be as bad as for smooth manifolds, right? Like, intersection basically, as a topological space, has basically no structure whatsoever. Okay, so let me first state the theorem. So theorem is yes, if you compute the fiber product in all categories. So in particular, it's some kind of derived fiber product. So X is some kind of derived. And this time it's actually somewhat critical to do this, not over the gaseous real numbers, but over the liquid real numbers. For some choice of number 3. So this liquid structure depends on the parameter. That doesn't actually matter for this application. Yeah, so for everything else we did in our course, this kind of liquid structure that we once produced was very much effort. So not so relevant, but here I think it actually really is relevant for a reason I will explain in a second. So what's the theorem? So yeah, so we can define some kind of notion of some kind of, if you can look at analytic stacks in our setup that just have the property that locally it is possible to write them in such an intersection, and then one can canonically produce a virtual fundamental class on them. Okay, so so there are some symplectic experts present at MPI, in particular Nate Botman and Katrin Gerheim. And I kind of discussed this a little bit with them already, and I want to continue those discussions. But in particular, they made me aware that, like, even in this kind of simplest case, it's kind of surprising that this should work. So let me say why this is surprising. So let's consider the case where, like, those M1 and M2 are first. There's my picture over there. And then just assume you're in a local situation where you kind of have two things meeting at just one point. Right. Locally intersection with one point. And let's try to analyze what happens in the neighborhood. So in the best possible scenario, this intersection is transverse. You just get a point and it counts as, I don't know, plus or minus 1, depending on your orientations. I don't know, then the next worst scenario is if it's a square function, then, okay, this should be 0. And if it's like a cubic function there, then it should be again plus 1, and so on. And so this tells you that if it's vanishing to finite order, then basically it's clear that we're okay, right? Because I mean, we just need to remember the vanishing order of that function, and this will tell you whether this function crosses a line or it doesn't. But now, let's consider a situation as you can have for smooth manifolds with this somewhat tangent to infinite order. Something like x minus 1 over x squared. But then you can have a very similar function, which is sine of x times x minus 1 over x squared. And so what I'm claiming is that the locus where this function is 0, whatever that means, determines whether this function crosses the line or not. The claim is the vanishing locus of these functions. Just the vanishing locus determines I mean, distinguishes these two cases, in particular determines whether the function crosses a line.
In which category?
In our category.
Okay.
So let me make it slightly more explicit. That means like in classical geometric pictures, it's quite unclear what kind of structure you could give the vanishing. I mean, this intersection point, which knows it must in some sense must know more than all the derivatives of this function, because we will never be able to tell from all the derivatives. But it knows much less than the germ of this function. It really only knows the vanishing locus. So we classically would maybe try to use the whole germ of this function in order to remember whether it crosses or not. Right. So so what is the vanishing locus? Of say some T-infinity function from R to R. Let's assume it really just has an isolated zero at zero. So this vanishing locus in our general form is just the analytic spectrum of this algebra of T-infinity functions from R to R modulo the ideas generated by F. Whereas this thing here, I mean, it is a liquid. I mean, it's a special type of condensed R algebra. With the induced analytic ring structure. So analytic ring structure doesn't matter. It is a very funny one, though. I mean, if F would only vanish to finite order, then this would just be a truncated polynomial algebra. So F vanishes to order n. It's the isomorphic to R join and like order T, what's to the n. And so this is some nice algebra. But F vanishes to infinite order, then there's some funny non-separated thing. Oh, that's right. Not for non-Hausdorff classic. And so classically, you would have trouble and down this with a topology, but in the condensed world, I mean, it has a natural condensed structure. And so here's a proposition that tells you that this vanishing locus, someone knows about this. So if you have two functions at above, and there exists an isomorphism of liquid algebras between their quotients.
You mean analytic rings with the liquid?
Well, I mean, I don't need to put the analytic ring structure on them because it's just an induced one. So I can really just look at them as liquid algebras. Also, I mean, F is still non-zero divisor here under this assumption I made. So this is really still concentrated in degree zero, just not Hausdorff. So I don't have to say anything. So assume that these are isomorphic.
So the condensed set of C infinity R means that you have to define smooth functions from R cross a profinite set to R, and you do it in the usual way, yes?
Yeah, you can.
Either
you have to do a construction just completely internally in the condensed world, and it will produce the right condensed structure, or just remember that it's a Fréchet space, or it's a topological thing, and you can just pass to the condensed world afterwards. Those give you the right answer.
And the liquid thing doesn't change the condensed.
No, I mean, again, the liquid is just a condition, right? I mean, any of these.
So it satisfies the liquid condition.
Satisfy, yeah. So I mean, I could also just say isomorphism of condensed ones. They happen to be liquid, but.
Okay.
So assume this. Then actually f is g times u, where u is an inverted function. And so in particular, being an inverted function from R to R, it must either be everywhere positive or everywhere negative. And so multiplying by such a unit cannot change whether the function crosses the line or not.
No. But what happens if you rescale the function? You take the exponential e to the minus 1x squared, and then you take, let's say, instead of x, constant times x. So those things have different growth rate. It cannot be that you use different coordinates on R. It doesn't seem to be, it seems fishy, because the isomorphism is abstract, of condensed algebra is abstract.
Right, that's right, but still it's true.
But e to the minus 1 over x squared and e to the minus 1 over, let us say, maybe it's true in this example, but
it is true, the offer, it is true. So let me give a proof. So first of all, why do I stress the liquid so much? The liquid means that if you take C infinity functions on M1 and tensor them in the liquid sense, with liquid real numbers, with C infinity functions on some other real manifold M2, I mean, this definitely maps to C infinity functions on the product. But by computation that we spelled out in the complex geometry notes, I believe, like on nuclear Fichet spaces, the liquid tensor product is doing the expected thing. And so it actually is producing the C infinity functions on the product. But it's not true for the overall gas. There it would be some smaller thing.
But concretely, what does it mean? R liquid is a R, right? As set.
As set. I mean, R is just the usual condensed ring, yeah? I mean, real numbers. Okay. But then you put a different analytic ring structure there, which is much closer to asking that like the building blocks are some kind of locally convex things. They're not quite locally convex, they're just alpha locally convex versus alpha might be slightly less than one. Yeah. But you're very close to the locally convex setting. And so when you form these tensor products, you're basically allowing all locally convex combinations. And at least if you kind of have nuclear transition maps, then the precise kind of convexity you need actually it doesn't matter, so the limited works.
Okay.
So this is a derived tensor product of the,
yeah, so it would be derived. Yeah. It works. So this is a non-trivial computation that comes out right in the liquid world. And so from this you can deduce that if you take C infinity functions from R to R, that this is actually idempotent over RG on liquid kind of G. Where T is the usual coordinate. Yeah.
So maybe the isomorphism should be condensed R algebras with the coordinate in the proposition. Otherwise, I don't believe. If you don't have the coordinate.
So yeah, I mean, you can just no. I mean, I said that both of them have the isolated 0 at 0. Here.
Okay.
Both of them just have an isolate 0 at 0. That's what I use, but I don't use anything more than that.
Oh, but I get it. Okay, let's see what he's doing, but he's not.
All right, so let's analyze the situation. So let's assume we just have an abstract isomorphism. So for both of these admit a unique map to the real numbers, because you can classify all the maps from C infinity R to R. They're just given by real numbers, a variation of some real number, and only one of them f is equal to 0. So what is definitely true is that they have this unique evaluation map to the real numbers, and this must commute because in those cases the unique map. All right. And now I have R join T equal to 0. Nothing to here via the usual coordinates. All right, I mean, maybe I should start. It maps to C infinity R. That's not doing it. And so I get there. And so where does this T go to? Well, I mean, let's assume G is not just also vanishing to first order. Then, like, I mean, he has this unique map, and he also has a unique first infinitesimal neighborhood. So this must be a function that's not vanishing to first order here. Do you actually care about this? Maybe I don't care. All right, so I have this map, but okay, I also have this composite map. And of course, it has a quotient here. And if I want, I can also lift to here, right? Because I just need to lift my element T from here to here, and I can do that.
Yeah, so you get that F is equal to G times the unit after a change of coordinate. So it's G times the change of coordinate, composes the coordinate change times the unit.
The unit times the change of coordinate, the unit.
Okay,
No, G.
well, what I want to, let me call this algebra here. Just, I mean, let me call this here A and this here B. So what I want to claim that this map from R joint T to B. So this is a usual map. There exists a unique extension, which is just a condition.
Okay.
And so it is a module with an important thing. And
there is a unique extension in which sense? In the sense abstract rings or
no, I mean condensed. So it's idempotent in this sense here, right? So there can be at most one extension.
Okay.
Thing. And I claim it exists. And for this, it's enough to check that it exists here, but I can classify all maps from R joint T to here and say all of them do extend, right?
Okay, they do extend by just okay. Right.
And there it's okay. I mean, you really just need, the extension is necessarily unique, so you just need to prove existence. But this map is given by some C infinity function from R to R. But then any other C infinity function from R to R can just be evaluated there. So that works. Okay. So, so this means that this map from here to here, it factors uniquely to here. So you actually get this map, such a map here, where this commutes.
Okay.
But this is surjective, this is isomorphism, this is also a quotient, right? Okay, so maybe this is a real parameterization that Gamma wants me to incorporate all this time. Sorry. And at this point, basically, like both of these are compatibly a quotient of these three infinity functions from R to R. So and then the ideals must, for this presentation, must be the same. Anyways, I mean, so I think from there you can conclude at least that this property about f crossing the line is only g crossing the line, because so there is now this presentation. I'm not saying it right, but let me make a more philosophical point here, however. So there are some existing theorems, a series of like derived manifolds, but they proceed very differently. In particular, they consider some kind of algebras of functions, whereby in the definition, whenever you have a function, then you can kind of compose with any C infinity function from R to R. This is some kind of data they put on the rings. But this observation is telling you that these kind of funny derived quotients that we're getting, they happen to have the property that whenever you have a function, you can always canonically extend to C infinity functions. So they acquire the structure that for any function you can compose with a smooth function. But you don't need to have to put it in the beginning. Try to see if we can salvage what I was trying to say there. So this is the canonical map. So this is the canonical map. Put it in the map here.
Yeah, you use that probably.
And I mean, those things can be classified. These are just given by a usual smooth function from R to R. And so then, okay, there is a reparameterization, and so maybe you have to put a reparameterization in. Then it just makes a similar claim. Sorry.
I wanted to say the same thing. It's pretty faithful embedding of manifold algebras. So this is just pullback by smooth map.
Right. So yeah. Okay. Maybe absolutely. Okay, so right, but so some of the thing that makes this work is precisely this thing, that you do get these unique extensions to C-infinity function, because otherwise you cannot control the kind of C-infinity surjection from here to the C-infinity surjection from here. You wouldn't be able to compare. All right. All right. So let me now state some more abstracts here. Let's say F in locally compact Hausdorff space. And let's assume also it's kind of finite-dimensional matrices. Which is always satisfied when it's an intersection like that. Plus the sheaf of animated liquid algebras. OS. So there is locally the intersection it's locally isomorphic, but not with a given datum. So this is just a condition intersection of smooth manifolds. Then one can define.
So this is a family depending on S of smooth manifold or just constant intersection of smooth manifolds?
Hmm?
The intersection of smooth manifold is constant locally, or is it varying continuously?
No, I mean locally you can write, or an open subset of S can be written as such a Freiberg perfect.
Where the just so coming from the point.
Yeah, yeah.
Okay. S itself is no, okay. S itself, S with this is okay. Then one can define
an expected dimension. This G is a locally constant function, this integer coefficient, an orientation sheaf. Omega S, so this is a Z-local system. Right, and okay, so let me denote by pi from S to star, just the projection of locally compact Hausdorff spaces. And a virtual fundamental class of like S equals to structure sheaf. Also this depends on S. I mean, all of these depend on S. Which is a global section on S of the dualizing complex of tensor omega S to the north.
This makes sense, yes. This makes a lot of sense, and the idea is that you
Because in particular, if the expected dimension is 0, S is compact, and you choose an orientation. Omega SOS or fixed. I mean, assume it exists and fix one. Then you can define the fundamental class, global fundamental class, as some of the integral of the virtual fundamental class. As the global, I don't know, the count, signed count of SOS as the integral of the virtual fundamental class over S.
Okay.
So I mean, under d equal to 0 in this orientation, this goes away, and then you just, and if S is compact, you have a trace map that goes back to the integers. All right. So let me sketch the construction. And so basically, this is just the direct analog of the algebra geometric construction. So I think this was pioneered in the work of abelian and Barbara and Technique. Then many people worked on this, and I'm not an expert on this at all. The paper where I learned it from is some kind of algebra, I mean, analytic homology inclination, or I don't know, by Adil Khan. But the ideas, I think, will take way beyond. So what they define, first of all, is this what they I think call the intrinsic normal cone. And so this relies so they have some kind of intrinsic normal cone on F over S. That so what's described this. So the fibers are some of the fibers, and some of this corresponds to the cotangent complex. Of like OS over R. So in our world, I mean, first of all, you can somehow define such a derived intersection of like smooth things. But also, if you compute what this kind of cotangent complex does, that one can like abstractly define for C infinity functions, basically for the same reason that these tensor products came out right. Also, the cotangent complex comes out right for C infinity functions on a manifold. And then for such a derived tensor product, of course, you get things. So this is actually a perfect complex.
So what's the superscript on the L?
Liquid. And so here's some kind of molecular theoretic description of it. So actually, I just want to define this here as a locally compact Hausdorff space. Sorry, stack. let's say it's a condensed anima, so it's some kind of stacky version. Where some tangent directions give you stack directions. I mean, it's not really, don't need to go all the way down.
Only group wave, you don't need higher.
I don't need higher, yeah. So for
because the L itself is concentrated in degrees.
Exactly.
Okay, okay.
Yeah, sorry, yeah, that's perfect amplitude. Amplitude 0, 1.
So Delin already did it. Okay.
For compact Hausdorff space, or profile set if you want, T. Well, first of all, home from T to S. You can just regard this as a maps from unspec of the continuous functions from T to R to somehow let me call it unspec SOS. So that you can, by locally doing the spectrum of this algebra, you can build an analytic stack in our sense. And then if you evaluate this on just the continuous functions, you just get maps from T to the underlying set. But now I want to define what are the maps from T to this intrinsic code. And this can actually be defined as a map from a funny algebra. It's you take this guy and you mod out in the derived sense by 0. In other words, this is a tensor product. It's a continuous function from T to R. And then tensor over R, some kind of R join epsilon, where the degree of epsilon is equal to the homological degree 1. And some particular squares to 0.
But where the structure shift comes in? Okay, it's SOS, OS is there.
So here it doesn't really matter because it will always factor over pi 0 if you map to the continuous functions. But here the derived structure matters because we map to something derived. And there is a
okay. So in the first thing you can replace it by.
Well, the first thing, yeah, you can replace it by the kind of by 0 and even by the Hausdorff quotient because of the Hausdorff thing here. Here not. And just by deformation theory, you can analyze what does it take to lift the map from here to here. And it's just something in terms of a cotangent complex. And so you can realize that the fibers here have some kind of it's some kind of geometric incarnation. Of the due also cotangent complex. So all the tangent directions, they give you kind of stacky directions. And yeah, and if there's some kind of actual obstruction, this is kind of non-smooth part, and there's actually also some vector bundle directions. Yeah, so in particular, some kind of smooth map. Or you can understand it. And so, and yeah, right. So there's a cotangent complex, and like it's a perfect complex, so it has a kind of dimension, which is a difference between the vector bundle dimensions. And so this already gives you the expected dimension. If you somehow look at the rank of this guy. And this kind of situation here, this geometry here will also produce an orientation sheet for you. Just think about it. So actually, what you really need to produce is need the global section. So an element in this intrinsic normal Kono test with values in the that's the data you really need to produce. And now there's this really funny thing that let's take R as a condensed set here down here, and then one can write down something down which everywhere except at 0 it's just a point. But in this fiber at 0 you get this funny formness. So there's some kind of cone-esque deform, which lives over the real numbers, and which everywhere except at 0 is just a point. But then as you degenerate to the point, suddenly there's some very stacky thing, and you see this intrinsic cone here. So how's that defined?
Can I ask a naive question?
Yeah.
Is it the same phenomenon as you described before in the analytic stack of P1, where you compactify over the fixed point at infinity?
I don't understand the question. So let me just continue with this discussion.
Yeah, sure. It's a bit.
So let's define what is this deformed cone. So mapping T to there, this corresponds to, well, first of all, let me use G for safety because I'm not sure if I've used F before. It corresponds to a map from, like this should map to R. So first of all, corresponds to a continuous map from T to R. But once you have that, you can look at maps from the continuous function from T to R modulo G, right? To where, of course, if G is the 0 maps, then this is just recovering what I told you before. If G is non-zero, well, then if you quotient by an invertible function, this is just 0, so you're not getting it. This is no data. So you just get a point. But then if G is a function that's somewhere invertible, somewhere 0, then suddenly you have this kind of thing where this is producing some kind of gluing these things together. Okay? That's some kind of deformed guy. And now it's just some simple game with 6 functors to produce a class. Because basically, generically, you just have a canonical section here. It's just a point, right? And then you just degenerate that section. Let me try to do it. So consider the sheaf F, which is Python deformed upper string of Z. So So this guy here is shrinkable. And that's the only way I currently know how to check that is to use it. I assume that's a derived intersection of smooth manifolds. And for manifolds, it's true, and then it's stable under fiber products. In principle, you could probably produce this canonic virtual fundamental class with much smaller assumptions. The only thing you really need is that this map here is shrinkable. But then you can define this thing, which is a sheaf on furthest for the cone. And then, okay, so you have an open subset J, which is the cone away from 0, and then you have I, which is inclusion from the cone. And then you have some excision sequence for F. F maps to and here you have which is just I lower star of the pi cone of a streak of F. And then in particular, you get a boundary map here. And the boundary map just gives you the class you want. Right. Let's just say what's the Z. And
but then
that's always a degree shift I'm getting confused about, but it did work out.
Because the identification, the I per Schrick F, when you
sorry. Yeah, sorry. There's a shift by 1 appearing here because I'm pulled back from. Yeah, so there's a shift by plus or minus 1 here. -4. Because I take Z here on the real line and not pulled back from the point. Okay. And so then you get a map from the H0 of R without 0 Z towards this H0 we're interested in. And okay, so this is and then you take a class here which is 0 on one connected component and 1 on the other, and the image is what you're looking for.
Okay. By the way, is it true that this pi cone def is not just shrinkable but smooth?
No, I don't think so.
I would have guessed. Okay.
I don't think so. I mean, so this cone of S is some crazy thing, right? I mean, it's some kind of fiber-wise, it's some kind of vector bundle like thingy, but over this crazy S. I mean, this S is completely nasty in general. And so if this map was smooth and also like the fiber was smooth, but this has just no way of being smooth, I don't think.
Okay.
So I don't think this thing that appears here is invertible at all. But you can, I mean, you can still degenerate the tautological fundamental class on a point towards this cone using a little bit of 6-functor magic. And then yeah, this cone differs from the original space just by some kind of fiber bundles, which you can analyze and which give you both the dimension shift and the orientation shift. Okay. I'm over time. So let me see.
So I don't know if it belongs, but
talk about the perfect obstruction theories that usually go into.
Well, the perfect obstruction theories, isn't it just that there's this cotension complex that behaves well?
Right. Okay, that's just completely inbuilt in the 600.
Any further questions?
So what was the exponential shift sequence in the previous point for R, where you have GA locally analytic and GM local analytic, in which, and Z? So in which sense, so I believe that those exist as stacks, maybe with symmetric monoidal structure. So this is like an exact sequence of symmetric monoidal analytic stacks. So in which sense is it something like this, or
well, is it just
sense?
group? Yeah, I mean, these are group of commutative groups, right? And these are analytic stacks with a commutative group structure. And yes, I'm not quite sure what the question is. I mean, it's an exact,
okay.
I mean, all analytic stacks, they are by definition sheaves, and then now these are sheaves of abelian groups. They're
sheaves in the higher sense. Okay.
And then it's an
exact sequence of
which probably, strictly speaking, would again be a triangle, because there might be.
Okay. Maybe I'm not so familiar with the language, so it's just. But this is an unstable
Well, but the abelian group structure kind of puts it into a stable context, right?
Okay. They're all connective, and it is an exact sequence in the.
Well, but it's also surjective on the right, so it stays the triangle on the stable.
Okay.
Okay, thanks, Peter.
Yeah, all right.